We're going to talk about the hydrogenation of an alkene. Now, when you do the hydrogenation of an alkene, you're going to always be doing a syn addition. So in order to see this, I like to draw wedges and dashes along my alkene. So the two wedges I always have coming towards me, and the two dashes are going away from me. When I draw my alkene in this fashion, I'm not seeing the alkene in the plane of the board, but I'm looking at it at a 90-degree angle to the board. So the two wedges are coming towards you, and the two dashes are going away from you. And I like doing this so that whatever you are adding, you can see it adding in the plane of the board. And this is really helpful for seeing syn additions and anti-additions. And a hydrogenation reaction, when you do it, will always be done in a syn addition fashion. So you're going to be adding hydrogen in the presence of some metal catalyst, usually something like palladium or platinum. Now, it doesn't really matter what these groups are, so I'm going to just kind of make some things up here and make sure that they end up becoming chiral. So I'm going to put a couple of methyl groups on here, and in the back I'm going to put in a couple of ethyl groups. Okay. Now, in class, I've said that this is the swimming pool reaction. Your little alkene is completely flat because the two carbons in the double bond are sp2 hybridized. So they're flat. So you can either do a belly flop or a back flop onto the metal catalyst. So what you're going to literally have here is a metal catalyst. Now, in our case, we're saying this is palladium. And bound to it will be the hydrogens. Okay. They're literally bound to that metal surface. And this is a biphasic reaction because you have a liquid or gas state and you have this solid state. So there are two different phases of matter. Okay. So here is the alkene we had on the previous slide. I'm going to draw it in the exact same orientation we had a moment ago. You can draw it exactly opposite too. But what literally is going to happen at this moment in time is this double bond is going to break and it will pick up a hydrogen from the same side as this bond here breaks. Okay, and these bonds here are going to break as well. Okay. Now we're not going to talk about what's going on with the metal, but metals can undergo several different oxidation states. And so there's some oxidation reduction chemistry going on here that we're not going to spend a lot of time talking about. But what happens here in the end is that the orientation of what was the alkene stays exactly the same. So what was a wedge stays a wedge, and what was a dash stays a dash. Okay? So my methyl groups are still on the wedges. My ethyl groups are still on the dashes. But this has changed from an sp2 hybridized pair of carbons to a pair of sp3 hybridized carbons. And they now have hydrogen bound to them in this fashion. You could also see the other version, which we will talk about in more detail in chapter 7. But this is also a possibility because, like I told you a moment ago, it could do back flop or belly flop. It doesn't matter which side of the alkene actually comes in contact with the metal. I'm going to say ET because I'm running out of room, but that's the ethyl group there. I just don't have enough room. But you will have the syn addition where the two hydrogens add to the same side of the double bond. Now, once you've done that, you can rotate this sigma bond all you want. Okay? You can rotate it as much as you want, but even if you rotate it, it doesn't mean that you've done an anti-addition. I'm going to show that to you on the other slide. I don't want you thinking this is a different molecule. It's the same molecule in every way. Okay? But I am going to rotate that sigma bond. And when that gets rotated, the groups are going to move. So you do have to be aware of that if you do rotate this, the other positions do have to change. So I know the wedges and the dashes have changed locations at this point. But that's what happens if I rotate this sigma bond right in here. Okay, so I can rotate it around, but you still have a syn addition. I knew I drew this like it was anti, but if you look at the notes from class, you can see that this would not be the same as the antis you saw previously. And you can tell that because the ethyl group here and the methyl group here are both the wedges. So they've changed. And that's the whole point. This is different because they have changed. If it was truly an anti-addition, the methyl group would be where this ethyl group is over here on this side. And that's not the case. So it's literally just a rotation of the bond, not a switching of what's a wedge and what's a dash.